Dalton's law of partial pressures and mole fractions is actually quite simple. I actually think it's one of the simplest gas laws that we have, but it's very, very useful. So Dalton's law of partial pressure basically states that in a closed container, the total pressure is equal to the partial pressure of each gas mixture that's in there. So what do I mean by that? If I were talking about air, for example, air has makes up several different gases. So if I put air in a closed container, the total pressure exerted in that container is made up of the partial pressure of each gas that makes up air in that particular container. So we can look at it in terms of this right here and this right here, okay? So if, for example, if we have a 1 liter vessel that contains 0.215 moles of N2 gas and 0.0118 moles of H2 gas at 25.5 degrees Celsius, determine the partial pressure of each component and the total pressure of the vessel. So what we know is that the temperature is 298.65. That's literally taking the 25.5 degrees Celsius and adding 273.15 to it, and then applying the ideal gas law to find the pressure of each gas, then simply adding them together. So if we look at this, if we use the ideal gas law for each gas that's in there, there's N2 and H2 combined in a cylinder. They told us that the moles of N2 are 0.215. We know the moles of hydrogen gas. We know the temperature of both the gases. And we know the total vessel container size. It's 1 liter. So if we take the N2 and we say, okay, it was 0.215 moles. Remember, PV, actually, hang on, let me do this. PV equals nRT. If I solve for the pressure, we're simply going to get that. Okay, so P equals nRT over V. And we're going to do it for each gas. We know the moles of N2. We know R is the ideal gas constant. It doesn't change. They are both in a 1 liter vessel, and they are both at the same temperature. So by doing the math and saying N2 is 0.215 moles times the ideal gas law constant times the temperature in Kelvin, whole thing divided by the volume of the vessel, the pressure of N2 is 5.27 atm. If I do the exact same thing, 0.0118 moles of H2 times the ideal gas law times the temperature times the whole thing divided by the liter of the vessel, I'm going to get a pressure of 0.289 atm. That should make sense to you because there's much less moles of H2 than there are of N2. So it should make sense that the pressure exerted on it, the hydrogen gas's pressure exerting onto the vessel is significantly lower than that of the nitrogen gas. So once we have the partial pressure of each gas in the vessel, we simply add them together to get the total pressure in the vessel. Mole fraction has to do with the fractional piece of an individual mole divided by the total number of moles that are present. We represent mole fraction by X subscript I. In this case, I does not mean initial, it means individual. It means we're looking for an individual fractional piece of a gas and its moles compared to all the moles that are present. Okay, so the mole fraction of a mixture must be less than 1. How do you remember that? How do you know you did your math right and remember, oh, it's supposed to be less than 1? Because it's a fraction. A fraction is a decimal, and decimals are less than 1. Okay, the sum of all the mole fractions must equal 1, and the mole fraction is unitless. Oops, went the wrong way. Okay, so there's a couple of different ways we can find mole fraction. This one right here is the most common, but sometimes you're given different pieces of information. If we had found the mole fraction based on the example we just did, where we found the individual pressure and then the total pressure, we could have found the mole fraction by using, for example, the individual pressure of the which one was the higher one, the N2, and the total pressure, which we found to solve for the mole fraction. We had to find the pressure first, so it would have been more realistic to use this one on the previous problem to find the mole fraction, simply because we knew the total amount of moles and we knew the individual amount of moles. So on this one, if I had okay, if I had that, then we could simply say, all right, I'm going to find the mole fraction of this particular problem, and I'm going to find it just for N2. Okay, to do that, we would have to know the number of moles of N2, which we do, and we know the total number of moles for the whole thing because we can just simply add the 0.215 to 0.0118. So we know our total is 0.2268. I just added these two together, and we know that's going to equal 0.215. Okay, that's my beautiful I there, my subscripted I. So if I simply just take 0.215 and divide it by the 0.2268 times one, or I'm sorry, not times 100%. Sorry, I'm losing my mind. We're going to get a mole fraction of N2 to be 0.948. Okay? So we would be able to say the mole fraction of N2 in this particular problem is 0.948. So if we look at this example, calculate the mole fraction of nitrogen monoxide in a 10-liter gas cylinder at room temperature that contains 6.022 moles of N2 and in which the total pressure is 14.75 atm. Okay, so we got two gases in here, nitrogen monoxide and N2, nitrogen gas. We know the mole fraction of the nitrogen gas. Not the mole fraction, but we know the number of moles of the nitrogen gas. And we know the total pressure on the container. We know the temperature that both the gases are under. And we know the size vessel that both the gases are in. So what we have to do first is we have to find the total number of moles. And we're going to do that using the ideal gas law. So again, we know the pressure, we know the liters, we know the ideal gas constant, and we know the temperature. So we can solve for the total number of moles in the entire 10-liter vessel between the two gases simply by using the ideal gas law and then plugging and chugging. So 14.75 atm times 10 liters, whole thing divided by 0.08206 liters times 298.15 Kelvin. Okay, this allows temperature to cancel, atms to cancel, liters to cancel. I'm left with moles. Okay, now once I know the total number of moles and they gave me the moles of N2, I can solve for the moles of nitrogen monoxide by simple subtraction. So total number of moles right here, subtract the number of moles of nitrogen gas, and that gives us the number of moles of nitrogen monoxide. Now we simply use this equation here, plug and chug, and we get a mole fraction of 0.001. When we use these partial pressures to solve problems, I'm going to go through one of them, but I highly recommend you go through all the rest. We're going to use them in a way where we're literally either solving for the total pressure of an entire vessel, or we're solving for an individual partial pressure. It's just going to depend on the question and how they ask it. So when we use partial pressures, you don't have to memorize this. But again, if you're going to go into a Chem 2 seated course, I highly recommend you become familiar with water, specifically water, its partial pressures at 0 degrees Celsius and 100 degrees Celsius. I would almost memorize them. Now these are in torr, so converting them to ATM and memorizing that as well is very helpful. So here's an example. It says calcium metal reacts with water to produce hydrogen gas. There's your balanced chemical equation. Determine the mass of hydrogen gas produced at 25 degrees Celsius and 0.967 atm when 525 mils of the gas is collected over water. So we're given volume, we're given a temperature, we're given a pressure. I just want you to note they went ahead and converted here the volume from milliliters to liters. And we know at 25 degrees Celsius, the partial pressure of water is 23.8 torr. How do I know? Because I checked this chart. 25 degrees Celsius, 23.8 torr. You can easily convert that to ATM, which we need because we'll be using the ideal gas law. And it's, just divide by 760 because 1 ATM equals 760 torr. And then the molar mass of hydrogen gas is 2.016 grams per mole. So that's really all here. This is our given information. Some of it we had to calculate really quickly. Some of it was just flat out given. So we know that the total pressure of the solution minus the pressure of the water will give us the partial pressure of the hydrogen gas. Right? That's what we're doing here. This is kind of step one. If you remember, go back. We have in solution the vapor pressure over water. Above water, and this. So note we kind of ignored these because that's an actual aqueous solution, and this is a solid. So we ignored those. We're only looking at the partial pressure of water and the partial pressure of the hydrogen gas. Note it said the gas is collected over water. So when we take the total pressure minus the pressure of the water, it will give us the partial pressure of the hydrogen gas. So this was given in the problem. You'll see right here, it was given. This we got from looking at the table 2 slides ago and converting it from torr to ATM. So simple subtraction tells us that the hydrogen gas collected over water is that amount right there. That should make sense to you because it's just collected over water. So there's not a ton of vapor from the water above the surface of the water in order for it to, really be a lot. Okay? I'm just going to draw a picture and say that one more time. There's my beautiful beaker, and here's my water. At 25 degrees Celsius, which is room temperature-ish, okay, you would expect that there would be some vapor of water above here, but it's not much. If we kicked it up, say for example to 100 degrees Celsius, then we would expect to see much more water vapor above the surface of the liquid because 100 degrees Celsius is water's boiling point, okay? So it makes sense that the vapor pressure of the water that has escaped the surface of the water is not a lot at room temperature. So it makes sense that the hydrogen gas has a significantly higher vapor pressure than the water does. So once we have found the partial pressure of hydrogen gas in our little vessel, the next thing we can do is use the ideal gas law to find the number of moles of hydrogen gas. So again, that's taking PV equals nRT, solving for N. I just totally wrote this backwards. Sorry, guys. This is why I don't like to skip steps. So what we get is N equals PV over RT, okay? So our pressure, our size of our container, which was given in the problem, you'll see it was right there. Remember, we converted it to liters. And then the ideal gas law constant, and then the temperature converted to Kelvin. When we do the math and multiply the top divided by the whole bottom multiplied together, we get 2.01 times 10 to the minus 2 moles of the hydrogen gas. And from there, we can simply find the mass by converting moles to mass using the molar mass. And we get 0.0405 grams of hydrogen gas.